Hello everyone. In this video we will continue to examine topic 5.1 electric fields, and in particular to examine the electric field due to some common charge distributions. Okay, so I mentioned briefly, or in the last video, that the way we find the electric field at any particular point around multiple charges is by using this principle of superposition. In the slides to follow, there are several examples of that being done and being calculated. But before you do that, I would strongly recommend getting a sense of just the general field, the general structure. And the best way to do that is in a two-pronged technique. So here's what I'd recommend. I'd recommend you take a blank piece of paper and you draw a generic charge distribution. The three I'm going to highlight are two positive or two negative charges, a double charge, a positive and negative charge known as the electric dipole, okay, it's two poles, and this general structure known as a parallel plate capacitor. That's when you have parallel plates, sort of flat, uniform charge. Okay, you draw them on a piece of paper, one right after another, so you could simply draw them on a blank piece of paper like this, let's say, and then put your pencil on any particular point and follow this process. That is, write down or sketch the electric field due to one of the charges, then sketch the electric field due to the other, and then do a quick visual summation to get that net electric field. You can then, if you want, erase E1 and E2. And do this for a whole bunch of points. Okay, and what you'll get, you'll be able to check as a general structure using the simulation. Okay, so I'd encourage you to go ahead and do that. And if I were to do that here, I'd pull up the simulation, and after having looked at my sketch, I would say, okay, well, I've found the electric field here, and here, and here, and here, and here, and you get a sense of the field that way. That can be a really useful tool, okay? Now, I want to focus in on that second distribution because it is so important, okay? This second distribution is known as the electric dipole, and this turns out to be an incredibly important field structure for a lot of different purposes, all right? And it has some features. Okay, so think about the electric field here. Note that right in the middle it's not zero, and that's because the electric field due to that left charge is positive and pointing to the right, but the electric field due to that negative charge is negative, therefore in the direction of the charge, and also to the right. So it sort of adds up over here. Okay, notice that if I move my sensor along that vertical axis right between them, although it gets smaller, it always stays the same direction. Okay, and the reason for that is that if the electric field is up and to the right, and the electric field due to the positive charge is up and to the right, the electric field due to the negative charge is down and to the right, and they're both the same size, then the up and down parts cancel by symmetry, and the parts that are to the right add up. So what you get here is sort of this line in which the charges produce electric field that is always just to the right. Now, as you get closer to one of the charges than the other, the field starts to look just like the field due to that charge alone. But in this region where they're interacting, okay, you get that very distinct behavior. Notice that if we pick a random point, like right here, if it were just the positive charge alone, so I'm going to take this negative charge away, you can see it would be away, up and to the left. If I add this negative charge here, you can see the negative charge, although it's further away from that sensor, is still changing or adjusting the electric field at that point. In fact, it's sort of pulling that electric field, right, in quotes, towards itself a little bit. So an arrow just a little bit down and to the right in comparison to that sensor. I would really encourage you to play around with this, draw some different charge distributions, and even test yourself. So for example, if you had an arrangement like this, okay, something like this, you can put it up here and then say, all right, what would I expect the electric field to look like at different points? You can draw a quick sketch for yourself, okay? And then once you have your sketches, you can then show the electric field and sort of test your own intuition. Did it look kind of like the one that you see in the simulation? One more important charge distribution to look at is known as the parallel plate capacitor. I'm going to draw or use a simulation to produce sort of a facsimile of it. Okay, it's not perfect because I can't do anything but add some point charges here, but it's good enough for our purposes. So I'm making sort of a flat grid here, and I'm going to do the same with the negative charges on the bottom. Okay. You can see it changes the field every time I add them. And then I'm going to pull them a little bit further apart perhaps, and maybe add a few more actually, just so we get a better sense of what that field actually looks like. And so I'm going to add some more here. Okay, doesn't have to be perfect. And now, all right, we take a look at that field. And the thing to recognize is it kind of looks like that dipole, only it's sort of spread out a little bit. The other really crucial important thing to recognize is the field looks almost completely flat and straight, right in the middle as it goes from the positive to the negative, okay? Going directly from the positive to the negative. And in fact, okay, if this were a perfect parallel plate capacitor, that would be exactly true. So the field in this region would be exactly the same value, okay? Exactly the same value and pointed from positive to negative. At the edges of the capacitor, you get these curly Q edge effects. So it sort of points around and goes around from the positive to the negative like this. Okay, those are known as edge effects. But in the middle, the value is roughly constant. And all in the same direction. That's a super important thing because it means we have the ability, using a parallel plate capacitor, to make what's called a uniform electric field. Okay? A lot like the gravitational field above the surface of the Earth. So this uniform electric field is basically the same strength, right? And that I haven't proven. I've just sort of suggested that it's true and shown you the simulation. So I haven't proven that. But it has to do with the fact that the electric field from all these points here, okay, all kind of add up like this. All right, so if you add them, all those tiny little green arrows are the electric field from the different charges located in our plates. And when they add up, the ones that are a little bit to the left and the ones that are a little bit to the right more or less cancel out, even in sort of this region. They only perfectly cancel out right in the middle, but they pretty much cancel out as long as you're away from the edges. And that gives you sort of this constant total electric field. Notice if I bring that point a little closer to that positive plate, then the field contributions from the positive plate increase. But as it turns out, the field contributions from the negative plate decrease by exactly the same amount. And that's what gives us this uniform electric field. There's a better proof of this, although it relies on some more complicated mathematics. But suffice it to say that if I had an infinitely long parallel plate capacitor, then the field would be perfectly uniform. And even in practice, this gap tends to be in millimeters. This length tends to be on the order of centimeters. And so what that means is we can build parallel plate capacitors that are pretty close to perfect. Now, in the next couple of slides, there are some practice problems that allow you to practice calculating the electric field due to multiple charges, and I would encourage you to sort of work your way through them. I will post one video that examines the hardest of those problems. That would be example 16.9, which is the electric field above 2 point charges sort of distributed. But the other problems, I would encourage you simply to work through bit by bit, and you'll get a sense of how to go about calculating the electric field.